9.10, Taylor-Maclaurin series. We basically have touched upon this section already just by simply saying that if you have this polynomial written out, you can assume that the nth term will have this as a coefficient, but also that it can be written in summation formula like that. Goes on to say that it's a Taylor series if it's centered at C, and a Maclaurin series if it's centered at 0. So just to get right down to it, let's look at sine of x centered at C over 2. Create pattern of derivatives, and hopefully you remember that in order to do so, I like to see 4 derivatives. So the derivatives are cosine, then negative sine, then negative cosine, and finally positive sine. And it's within those 4 that the cycle begins to repeat itself. We're going to evaluate each of those at pi over 2, and I'm running a little bit out of room, so I'm just going to assume that each of those had pi over 2 substituted inside. I'm going to do this without a calculator, and if you need to know, that's 90 degrees, and 90 degrees falls in our interval as the last in the chart. So I don't even need to fill out the whole chart. I already know what positionally goes in each place. This is increasing till it gets to 1, and this is increasing from the right side to the left, starting at 0. So sine of pi over 2 is 1. Negative sine would be negative 1. And the cosines are both 0. Plugging into the series, remember I get my original term times x minus pi over 2, where I'm centered, to the 0 over 0 factorial. Next coefficient times x minus pi over 2 to the 1 over 1 factorial. Next coefficient times x minus pi over 2 squared over 2 factorial. Next coefficient, x minus pi over 2 cubed over 3 factorial. And the last coefficient times x minus pi over 2 to the 4th over 4 factorial. The cube is gone. The first power is gone because they both had a coefficient of 0. And what I'm left with is, well, this entire first term turns into 1. The next term turns into minus x minus pi over 2 squared over 2. And then plus x minus pi over 2 to the 4th over 24. This is just the first 3 terms. I say 3 terms. It's not the first 3 original terms, but these are the first 3 existing terms. Can we create a polynomial from that, or a series from that formula? Can we be creative enough to figure out what patterns exist? Well, you'll notice that the even terms are the ones that exist. If we start at, let's see, how did we do this before? We start at 0. No, we don't want to start at 0. If we start at 1 and go to infinity, then first of all, it is alternating. Well, let's start at 0. It's alternating, but the first one is positive. So if I plug in n, I will get a positive number. I definitely have x minus pi over 2. That part's easy. And whatever I get from my exponent, my denominator is going to match. Well, 0, 2, 4, 6, it's even numbers. If I put in 2n, if I plug in 0, do I get 0 like I need it? If I plug in 1, do I get 2 like I need it? If I plug in 2, right, 0, 1, 2, do I get 4 like I need it? And I do. Okay, this right here, in other words, is called your Taylor series because it's written in summation formula. Again, there could be some adjustments. If you had a 1 here, you would see a difference in your exponents. But by putting in 0 here, I was able to get everything to check out. Okay, Taylor series because it's pi over 2 that we're centered about, not 0. All right, so let's keep going. Determine the interval of convergence. So again, our series is from 0 to infinity. It's -1 to the n times x minus pi over 2 to the 2n over 2n factorial. The interval of convergence would be, well, if this was a power series, I would use a geometric formula. But because it's not, I'm going to use the ratio test. Which can look awfully confusing if you're trying to understand it as quickly as I write it sometimes. So like I said before, pause me as you go and make sure that each of these steps makes sense. Before I start going through and canceling things, I'm going to simplify my exponents here. I suppose I could have written x. Yeah, I will. This is 2n plus 2, so it's to the 2n, and then to the 2. I always write my smaller factorial. I leave my smaller factorial alone. This is 2n plus 2 times 2n plus 1 times 2n factorial. I've got -1 to the n, and I've got x minus pi over 2 to the 2n. Goodbye, 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 goodbye. I have my exponent up here. It is finite. My denominator is growing toward infinity. This will be convergent as long as it is less than 1. Well, this all turns into 0, and 0 is always less than 1. Okay, so if that's convergent regardless of the x value that I use, then I know that my interval of convergence is -infinity to infinity, and if they asked, which they didn't, my ratio of convergence would be infinity. Okay, 2 very important pieces of information. That's all you have to do. It looks so much like a previous lesson that it shouldn't be that big of a deal. Maclaurin series for the following: cosine of x squared. Okay, now it gets a little bit interesting. So here's what I do know. We just did sine. In a previous lesson, did we do cosine? That's what I want to know. And I'm not seeing it. Give me just a moment here. I've got one more lesson to look at. Cosine, cosine, cosine. Let's see, sine. Okay, yes. This is what we came up with for f of x equals cosine of x. Now this is important, okay? We came up with (0 to infinity) of -1 raised to the n of x to the 2n over 2n factorial. Double check that, because that looks a little bit interesting right now. over 2. Okay. Okay. So just to keep you up with where my brain was, I thought this looks a lot like what we just did over here, right? We just did sine at 90 degrees and we came up with that formula. So why would sine of 90 degrees look like a formula we did a while ago for cosine at 0? Well, if you remember, like we just did, at 90 degrees, our cosine was 0. And at, sorry, I'm saying this all backwards. At 0 degrees, our cosine is 1, and at 90 degrees, our sine is 1. So they are going to match here if this was just cosine of x. But it's not. So what do we do if we have cosine of x squared? Is there a shortcut that we can use? Well, this, if we plug in each of these numbers, if I plug in 0, I get a positive x to the 0 over 0. Okay. If I plug in 1, I get negative x squared over 2. If I plug in 2, I get positive x to the 4th over 24. If I plug in 3, I get negative x to the 6th over 120. Positive, so on. I think 6 was that. 720, sorry. Okay. So if I want to quickly figure out my Maclaurin series, and I already happen to have my series for cosine, then the easiest way to go through this process would just be replace x squared with the x's that were already there. So the series was fairly easy to generate. The formula is going to be very easy to generate as well. It's my original formula, but my x is going to be squared, so this becomes x to the 2n squared. Actually, what I should have done, sorry, I should have written it as x squared to the 2n, giving me negative 1 to the n, x to the 4n, all over 2n factorial. And that's just a shortcut way to come up with a formula without having to do all of the derivatives, finding the patterns, and so on and so forth. You are unlikely to be tested on something like that. But I say that, I might have to take that back. But anyway. Sorry, that was simplifying the process. So what you could have done is the long way, and I didn't want to do that to you. All right, this is it. Last video question. Chapter 10 is going to look a little bit different, so this might be the last video altogether. Find the Maclaurin series for e to the 2x and determine the interval of convergence. All right, e to the x should look familiar. E to the x was the series, and I'm going to go back and look at my notes just like I would expect you to do as well. Besides, you get to use your notes during the test anyway. There it is, e to the x, x to the n over n factorial. Okay, so that means that if I had e to the 2x, that should be the same, as putting 2x, oh my word, what am I doing? 2x in for x, right? That makes sense. Okay, so It says we're going to look at the interval of convergence from here. This is not a geometric formula.